argument due to nothing that we're doing. But we generally like to believe that any really big can never.
Okay, if you're just tuning in now, it has not started giving us a presentation. Hopefully we have it going on. And
as long as Cave is here in the United States of America, it's Mammoth Cave in Kentucky, and Mammoth Cave Park. Mammoth Cave is composed of many different caves, been linked over the years. Exploration is done in, I think, running about 6 expeditions a year there for the Mammoth Cave system. But there's a whole bunch of other caves surrounding, and there is a possibility, geologically possible, that some of these other caves, Fisher Ridge being the biggest one, 20 miles in length right now, we have reason to believe they are not fully connected. It may be within our lifetimes that some more of these connect in. So the 100 to 1,000 mile caves in one single system in central Kentucky. But coming up fast on Mammoth Cave are these incredible caves.
Sound and pictures. Thank you, Barbara.
Which are all, or almost all, I pushed my button accidentally here. Well, I'll shut up. Anyway, these caves are pretty close.
Well, are we ready?
I'm as ready as I'm going to get.
Perfect. Well, welcome everyone to the Tucson Mineral Gallery on this lovely Friday morning. My name is Downey, and without any further ado, I'd love to introduce Kevin Downey and his talk on what's new underground. So without any more delays, Kevin, take it away.
Thanks. Well, I'm going to talk really fast. I'm going to try to show a lot of things. I'm going to try to hopefully make it entertaining. This is a semi-talk, but the idea is to show a lot of new things. A couple of surprises in here, so we'll get to that in a bit. But basically, this is a talk on cave minerals, in particular about the minerals that we understand, what we can understand about them, and a little bit of why we think they're incredibly important. And finally, I do have to mention, since we're all deeply involved in the mineral world here, as people studying minerals and enjoying minerals, that all of the caves are being kept as pristine as possible, which means we're not collecting anything. We're studying, we're collecting these things with cameras and with studies, but we're leaving them as intact as it can possibly be done for future. So this is our heritage, and they're completely irreplaceable. When you see what we're looking at here, I think you'll come to understand why they're so incredibly special. So this is fairly new. As a new frontier, people have looked at cave mineral a long, long time, but the idea that it's actually a little bit of its own science is really something quite new. So to start off, we have to talk a little bit about caves, just caves and where they come from and what they are, and then we're going to jump into minerals. But I don't want to start off any misunderstanding. The nature of caves are, first of all, the definition is that they're completely natural. There's no mind. This is all made by natural processes. They have to be large enough to admit a human being, otherwise it's a bug or a pocket or something else. They can be quite extensive, they can be quite diversified, they can be above or below water, but caves occur all over the world in all sorts of different bedrocks. The contents of the caves can be really exceptional and amazing, and I think you'll come to know this. A lot of I'm going to show minerals within the caves are actually incredibly rare things. So there. Anyway, the last thing I want to talk about, get into the caves themselves, is these. And it turns out that we can form caves in practically any kind of bedrock. Overwhelmingly, caves are formed in carbonate bedrocks, the things form some dolomites, other things formed in shallow seas, distributed all over the world. We have these karst areas, which are, areas with subterranean drainage, which is super exciting and interesting to us. However, this isn't are often uplifted, and a good percentage of high mountains, especially the Alps and so on, we've got these nice high limestones where you've got these well-developed systems at great depth. The tropics with heavy rainfall tends to dissolve the limestone much quicker. It creates these wonderful and strange bits of landscapes, and some of them are very strange. Right. Well, this isn't moving forward. There we go. Not all are formed in carbonate bedrock. Some of the world's great caves are formed in lavas and volcanic rocks. Mount Fuji, which is lots and lots of lava caves formed not only on the mountain, but in far-flung areas where the lava flows are quite deep. And there's also caves formed in marbles, which are very much a harder type of rock. They dissolve just as well. This is a view in one of the caves beneath Mount Fuji. These are speleothems formed. It was molten lava. They're which is caves literally in which they're for a number of reasons. Strange things. Very few people have seen a cave formed in Nice or not. And it is an interesting bedrock, very strange structure, interesting caves. There's caves formed in quartzites, which tend to have really strange and unusual, extremely hot rising waters. Some examples of these things. There's caves formed in sandstones, especially sandstones that have carbonate within their stones, which can be dissolved under certain conditions and form substantial cave networks, some of which are really quite mysterious and unlike other caves on the planet. So, caves are everywhere, worldwide, happen to be of different. And each of these different bedrocks tends to give caves a very different characteristic and also provide a bunch of different elements which are responsible for the formation of the minerals we're going to be looking at. This is a bit of a strange cave. There's actually a whole series of these formed. Garrotite, these are iron caves. They're called iron ore caves because nearby are iron mines chewing it up. That's their ore. These caves actually contain, and this is, a lot of people are unaware that used to be native iron. Iron was a pretty rare item. If you collect native elements, you probably have seen, have a few examples of native iron. Just a small number of places. Some of these caves, a single cave will go every mineral collection on. It's quite impressive. And also a lot of strange secondaries do form in the iron ore. So most of the caves that we work with are highly modified or dealt with by water. Basically works its way underground through all systems. It can start from the surface and work its way down cracks. It can rise from extremely deep beneath the earth. So we have rising waters, we have shrinking waters, and of course, the obvious path, the obvious function is to build caves, and caves can and often are conduits. The only place in the world you can imagine you can have a river underground, and then you could have houses that river somewhat deeper, and they have no ascend in a spiral and flow underneath themselves. So different kind of three-dimensional maze. And this is not moving, so let's... Anyhow, water and rock, that's the main event. Water, of course, depending on its condition, depending on the nature of the bedrock, and especially we'll show examples of carbonate caves, sculptures. Some of them are, of course, the very small structure. Everybody who does much caving has to come to grips with the fact that a little tiny places you get to pass through. This is my favorite spots. It's a passage called the Gun Barrel. It's 55 feet long. That's the biggest part of it, and people pass through this every so often, and great that they got through it, but then they have to return the same way, and it's a little bit of a psychological challenge for some people. We also get lots and lots of voids that can be of quite big size. I think this thing is a pointer here. Well, anyway, just to give a sense, here's a surface down to this lake. So it's the development of single rope techniques that allowed us to get to lots of places that were never possible to get to before. And it's really exploded the world of cave exploration. By the way, a lot of these techniques are useful in exploring old mines.
Is that time-lapse?
It's a single-person climb, 86-foot pit. It's in the state of Georgia, northern Georgia, inside of Pigeon Mountain, and it's a fantastic, and the name is very original, pit. Anyway, isn't going as fast as I. Each of these different solutional structures, we get scallop marks and we get solutional pockets and so on. And the experience those pockets here are in fact formed by a mixture of saline waters or salt waters and fresh waters. That tells us a little bit that we're in a cave that was by both, in this case, ocean water and fresh water together. And let me see if this button works better than that button. I think so. All right. So I'll kind of zip along here. Hopefully everybody will wide awake. Rising waters do some different things to limestones and other carbonate bedrocks. And this sort of joint, you see all these little cracks and so on. You see being deposited in these. You see all these things. It actually looks in some cases like what would be even bedrock. This actually does contain a tiny amount of sulfide here, but it's really not a. This is a fully natural cave, and this is just remnants. But it gives an idea of the structure of rising hot waters. And of course, many caves are formed on different levels, networks at different horizons. And the remaining bits of bedrock will tell their story. And then, of course, we get to have deposits with it. Many people are very familiar with stalactites and stalagmites, which is a very well-known feature. We're going to talk almost not at all about these. I think most people understand them and seeing them. Part of what we try to do is make as accurate as possible maps and plans and profile for all the caves that we work in. And some of them are quite complicated and in many cases confusing. Drawing a map while you're exploring a cave is a little bit like trying to draw the inside of a sponge while you're inside the sponge. Anyway, despite the fact that there's very tiny print of you, this is about water, and it is certainly the most dynamic cave mineral, and it is a mineral, so we'll include it in the talk. Why not? Anyhow, water comes into caves in many different ways, and it does many. It can be basic, it can be acidic, can be deep, shallow, it can be fast moving, slow moving. It is the environment work with in caves, and very few caves are now so old, much deeper, and we only see water if there's a flooding event or rising water under. But when water is captured in pools and shallow basins and so on, this begins one of the very first phases of mineralization, where you have deposition at the interfaces of pools and other conditions, and calcites forming. And issues with water has to do with terrain. We have hot waters, warm waters, and incredibly cold water, snow melt and ice melt. They totally behave differently, and they have a different impact on chemistry and, of course, within the minerals. Moving waters, especially fast-moving waters, behave very different than still waters. They have very little time to degas, they have very little time to develop things, but they can in structures and also modify them at a fairly fast rate. Nearly every speleothem we're going to look at has some, and one of the things I find most fascinating is the fact that even very tiny needle-like crystals have a tiny central canal which allow water to seep upwards or sideways along these tiny central canals in incredibly amounts, eventually condensing into droplets. And there you see the size of water droplets growing on calcite and aragonite needles. Big, as you've already seen, the big cave lakes. And then we have this whole world that takes place just underneath the water surface. There's a whole other world of civilization that doesn't take place in fresh air. It can grow underwater, and the way to see this is, of course, scuba techniques. Gets us into some interesting situations. As I mentioned earlier, before, some of the world's largest caves, 100% underwater, and the exploration techniques to get these long distances and stay for long have really been developing very fast over the last few years. All right. This text is pretty self-explanatory. If you want to understand caves, pretty much need, and their always have is, how did they get there and why are they there? Normal cave minerals, stalactites and stalagmites, beautiful, wonderful, cool things, but kind of normal. Of the stalactites that are out a little bit abnormal, these are extreme, we call them straws. They're calcite formed in this way. They're incredibly and very cool, but they are not all that rare and weird. They're very cool and are quite dead. But the other things start forming in other ways, and they take on. So I'm going to just give you a quick idea of some of the nature of the depositions and utilizations we find in various caves. Here you see a series of stalactites. We're kind of on the normal side, and a former pool level. Here you can see the former water level. And right next to each other, for some strange reason, you have several different habits of calcite growing in exactly the same water. And the question as to why and how did this happen? Why aren't they all the same? And these are good questions. I could talk all day about them, but we're going to jump off and brief for the moment, but give you some idea of things that we don't really fully understand. Many of these form a spot on the entire planet are not replicated anyplace else. The calcites take a variety of forms, and even when this is forms we call helictites. They're really magnificently complicated calcium carbonates. They can be either or aragonite, occasionally other minerals as well. They are not super rare. Such displays as this are extremely fragile. and why these will form in linear structure, patterns, and so on. Not a whole lot of answers yet, because there's this, so rather selective deposits. These are also what you see here in these long tendrils. They are all hollow. They do drip water. And then we have other calcite forms. We're going to look at a few cave pearls in a moment, but just to give you an idea what's there. And the variety and forms of calcite within caves is just endlessly fascinating. And these are, to my taste anyway, some of the world's greatest mineral treasures. Not something you'll ever see unless you do the effort and get there yourself, which is a great motivator for a lot of people. Some idea of some of the strange things. There's some scalenohedral calcite crystals in a former pool. Growing from the tip or termination of one is a helictite, hollow, growing from the tip upwards. And then there's another one that's growing off from the side. It makes a half circle around the other one without touching it. They're just delicately in balance, but each other at all. Again, calcite forms, infinite number of varieties, and lots of strange variations. Start to get into things that we just don't understand, and very little is understood about these blue tip helites. There are some interesting studies that are going on, and at one time we used to say, oh, well, there's some water filled with a lot of copper carbonates or copper secondary minerals. Turns out, after a lot of care and doing some very delicate analysis in context, there's no copper involved. There is some zinc, a little bit uranium, a little bit lead. Very, very weird. We don't really have a great understanding as to why these things have the colors that they do. A fair number of mineral species that are in caves. I'm going to jump over a few of them. We have a small number of elements, and that's a growing number, actually. It's one of the exciting things. But an awful lot of everything from arsenides and so on. We tally up now, we're getting to around 380 species that are, and by the way, when we talk about cave minerals, we're talking about minerals that form in the caves. These are not minerals that were already sitting in the limestone or bedrock and they were exposed. So we have caves, for example, in the Adirondack Mountains where you have crystals of scapolite and corundum crystals. Those crystals formed in the bedrock long before the cave was there. And so the cave had nothing to do with them except the solution of the cave exposed them. So we don't count those as cave minerals. These are minerals that formed there because of the cave environment itself. So a lot of strange things. There's things like allophane and a number of strange secondaries. You'll get copper-rich opals in some of these places. A lot of sulfates that form in contact in conjunction with carbonate rocks and forming in different sequences, depositions that are sometimes related to former water levels. Gypsum we see a lot of in selenite forms. We'll see a few more examples of these. We call these things chandeliers. This is from Lechuguilla Cave in New Mexico, which has been one of the great cave discoveries of the last century or so. And again, loads of variation form. This is a not so common cave secondary mineral, the crystals of dolomite, and they're quite large. The biggest of these are getting pretty close to 10 centimeters, very sharp, kind of similar to some of the ones that are known from Spain long ago. And this is, by the way, in a passage in a cave in Cuba, which was named, the Spanish word for it is the Ich Uch Ouch passage, simply because you have to crawl through here. And it really hurts, even wearing knee pads and so on. And it translates really well. But we tried very hard to avoid damaging or touching these things. We have a very narrow little way to go, and there's just certain places where you can put your foot and your knee and gently work your way through so that the area is preserved. Things I mentioned, native elements. Sulfur is that uncommon, especially in caves with huge amounts of sulfates. There's a number of other elements, but one of the big surprises for those of you who follow native elements is the world's second discovery of native aluminum in a cave in Venezuela. Native aluminum is an incredibly rare thing because there's only 2 discoveries. And the cave in Venezuela has the first and only examples of native aluminum crystals. The others are massive. We believe, but we're not certain, that there's a microorganism process which is basically extracting native aluminum from some of the minerals which are already in the bedrock. And this process is very interesting to people in the aluminum business, because if you can come up with a microorganism that refines aluminum, it could be a very cool thing, and you wouldn't need to use huge amounts of electricity to do it. Other strange minerals, epsomites, and other such things. This is one of my favorite scale objects. It's a life-size goose. I just got tired of using people for scale objects all these years. But these are wonderful crystals of the mineral epsomite, mirabilite, and so on can form in similar ways. They're also a very cool native, they're also a really effective appetizer. They're a diuretic, and they're useful if you are having difficulty digesting food. And the Native Americans in our region would go into caves to use this as a local medicine quite a bit. This is metatiamonite in a cave in New Mexico. And again, many of the strange and interesting, and in some cases quite rare copper minerals. And then here you see a sequence of alterations where you get a slight alteration, especially as zinc increasing and decreasing. These things are very fun. Again, iron, secondary minerals, goethite, hematites, and so on. And one of my favorites, a very strange and quite rare mineral, hydromagnesite, forming in balloons. And these are balloons. They're not big, a maximum size about 6 centimeters, but they're calcium with carbon dioxide gas. They blow up to a certain size, stay there for a while, can deflate and reinflate time, and then eventually they rupture and they will to aragonite. This one is not yet ruptured to aragonite, it's partly filled. And it gives you some of this strange and interesting mineral. It looks like, in this cave context, there's almost certain microorganism process that's helping to generate the CO2 gas, which is inflating balloons. It doesn't exist any place on the planet except on a number of minerals which are quasi-organic or superorganic. These are not normal stalactites. It's just a very rare form of bat, a very, very sticky type of guano that in very tiny colonies on the ceilings. This is a particular bat in an area of southern Brazil. Guano coagulates, and then over time begins to alter a fair amount, and then you get things like fragipontite, so on, some of these interesting minerals, a number of phosphates found growing in and on these things. It's just weird genesis minerals. This is a small percentage of caves in the world are formed out of beds of halite, oftentimes interbedded between caves that you can eat your way through if you had to, is to demonstrate something that isn't in the photo at all. There's some wonderful caves in Africa where there's large exposed areas of halite in very dry areas, and a number of animals, including elephants, will travel long distances to lick the halite. Over incredibly long periods of time, by their tongues, they have developed caves large enough for elephants to walk into and go, in some cases, a couple of 100 meters back, where they are licking away the freshly exposed halite at the end of the cave. And they have to go, they don't get to turn around and walk out, they have to walk out backwards. While they're there, they also defecate and urinate, adding some more chemicals to the whole mix in the cave. So there's a number of minerals found in the elephant feces and urine pools of elephants that are unique to these caves on Earth. So just, I don't have any pictures of the elephants licking their way through a cave. This is the best I could do. A quick example of some, well, a lot of folks know Smith's oftentimes, well, not oftentimes, but occasionally with the nice yellow color, which we often attribute to cadmium, which in this case I believe is cadmium, but it could, it's not. Pools, especially after you get all kinds of interesting interactions between some of these minerals, sometimes on a microscopic level. Interfacing along with guanos, it forms a number of different clays and other things which are quite interesting, and yeah. Anyhow, this is a non-scientific photo, but it's one of the fun parts of cave exploration. We do get a contact with gooey muds and organic stuff, and you have to love it or you're not going to be into it very long. More and more examples of things. When this was first, this particular cave in South everyone said, oh, this cave's got all kinds of malachites in it. It turns out there's not a speck of copper in any of these mineralizations. There are calcites here, aragonites, and so on, but the color is all due to zinc, and in some cases we have, well, we have zinc, we have nickel, and we have cobalt. The nickel is probably the predominant chromophore here, but there's more zinc than there is. It's weird and strange and kind of and then we get second, and then we get other caves formations, very beautiful things, which are in blues and blue-greens and other things, and secondary minerals on top of secondary minerals, many of which are still being studied. A number of new species are coming along, and a lot of these seem to be somehow connected to microorganisms. These are aragonites, intensely blue, and there is not a speck of copper in these. You saw a different this photo a few moments ago. These are real in our world. We really go to great efforts to preserve them, protect them, and it's sort of like it's like going to church or something, you know. This is a very special kind of thing, and a great honor to work in caves with such delicate things. So anyway, as I mentioned, water moving through are very cool and different things. So to get just a little bit of an idea of how some of this stuff can actually change just with some velocities and over time. This is something we like to call conulite. They're formed by points, times within dissolved clays, which then crystallize out and form various sorts of cups and cones. Others dripping on already pre-existing calcites can do a number of things in terms of making modifications. And moving air while things are growing can all kinds of exotic distortion, as in this case. And not a lot of moving air, in fact, fairly high CO2 environments. We then get speleothems with lots of these really exotic things, and in many cases, the terminations or the endpoints of these, which are all calcium carbonate up until you get to those white areas near the tips. And in those white areas, you can get all kinds of other stuff, including some other carbonate rocks, and a few phosphates can be forming there. Slight differences in water chemistry can obviously change color, and basically water can move through incredibly spaces, especially if there's some pressure behind it. And the developments, like this little freestanding helictite with a drop of water at its tip, gives some idea of the power of water through capillary channels. As crystallize rather slowly, we can begin twisted or corkscrew forms, or basically stacks of rhombohedral crystals, which to create the shape there. You see the light highlights along the edge. Standing needle, that's just for flowing water. Directions like this can create other deposits, some of which are fun and interesting. And I mentioned that little drip of water gives some scale to this whole. Corkscrew formations, basically because of the potential for calcite to form in stacking crystals, which are rhombohedral in nature, allows there to be a structure which forces the water to follow a corkscrew-like path, and we can get things like this. This also has a corkscrew, however, these are crystals of halite. Again, it's salt growing within caves. This is under the Atacama Desert. And also under the Atacama Desert, halite in caves loves to form cubic or octahedral crystals, likes to be epitaxial and forms structures that are very cubic in its nature. Native, or not native, it's just halite, but it's halite growing in a cave environment. And all kinds of other depositions. I'm going to jump into a slightly different topic here, looking at some of the water and below the water, which is really where a lot of action takes place mineralogically. And hopefully no one's snoring yet, so I'll just keep on talking. This is basically most caves have at some point, if they're reasonably good size, you will eventually encounter what we call the water table. And sometimes there are several water tables, perch water tables at different elevations. They may or may not connect with each other. Once you get to these water tables, if the water is still enough, we begin to get some really cool things happening. And here you see floating rafts of calcite crystal. Now, calcite, of course, is more dense than water. If it forms like a snowflake on the surface of the water, it can continue crystallizing out just like a snowflake, and snowflakes will interconnect with each other. And this calcite will float. We can also get calcite coating water bubbles. We get floating bubbles of calcite in some of these pools. As long as a pool isn't disturbed, and this can go on for thousands of years, this will slowly crystallize out. It can crystallize out so long and get so that eventually bits of it break loose, fall to the bottom of the pool, and create what we call raft litter. While it's underwater, it can continue while it's there. This is something that's happening here. They would have been too thick to have been floating, but once they sank, they can continue as basically broken pieces of calcite rafts, continue crystallizing outwards and get a little thicker, a little bigger. Now this process gets kind of interesting when you have really big lakes, and then occasionally along the way drip points will be forming. So this is a quite large lake. I've been doing some work on this place. It's in Brazil. There's some cones out of the water, and they may look at first glance like they're stalagmites, which is something pretty normal. They are, however, not really stalagmites. These raft cones, where there's been a drift, of the floating rafts, and it continually breaks them more rapidly at these points. And so underneath those drips forms a pile of litter which crystallizes together. And some of these things get quite enormous and elaborate and very cool. This is something very, very special to experience, these forests of raft. It also happens in these pools that there's a number of other things that can be going on. This is an example of what we call subaqueous helictites. Helictites, like what you were looking at before, except that they form underwater and not out in the air. Formed by a different method. It's called the common effect, which is not something we'll go into for the purpose of this talk, but it's a very cool around the world. But when they do grow underwater, they can form in structures. And then, of course, if you want to combine these with a pool, which has both subaqueous helictites and floating raft cones, you can get the helictite bushes decorated with the raft cones, which are now crystallized together. And this is about 60 centimeters in height. So it's, you know, a couple feet of subaqueous helictite. Also growing underwater, depending on the depth of the water, temperature water, and mixtures of other chemicals influence the water, it will determine what is the nature of the calcite that's going to be crystallizing there. And this calcite is actually influenced by the presence of magnesium. Then to just kind of stay on this weird topic in pools, these are crystals which were first seen in a remote part of Lechuga Cave in New Mexico. The guys who first found them looked into this pool and said, hey, there's these clear glass-like crystals growing in this pool. They're like prisms. There are rainbows in them. And they didn't know what they were for sure. They named them dilithium crystals, which if anybody's old enough to remember Star Trek, that's a totally good name. However, these are highly transparent prismatic gypsum crystals growing in these pools. A little bit closer idea of what they're like. They don't get super big. Largest of these is about 25, 30 centimeters, but most are much smaller. Extremely perfect and growing in just sort of a random mixture. And some pools will form this and other pools all around don't. Really good question, and I don't really have a perfect answer. And at the waterline, especially once the water's gone, secondary mineralization, deposition at these interfaces can form really interesting structures. And both you can see the influence of being underwater and then later on being exposed. And then some of the more exotic we call U-loops. These are essentially calcite forming after bacterial colonies. And this is pretty close to, I think, well, quite a number of kilometers from the nearest entrance by travel time. Maybe 8 hours of moving quickly to reach this point. So this is from an influence of the entrance to this cave. The pools, as they dry up or as water coats and slides over things, allow all kinds of interesting things on these floors. And secondary deposits, and then secondary and tertiary deposits growing after one. And some of these places in interesting cups of different, these are circular or semicircular cups. They are essentially cones, or thrown into these cones. Some cases you get rather elaborate crystals forming on top of botryoid forms. And again, branching structures, different types. It can be pretty enormous things. Oops, we went a little too fast there. Crystallization below the water. And one of the stranger things that a lot of discussion and argument about, shouldn't do that, are what we call folia. These are inverted cup-like structures. They're upside down hollows that form in certain interesting conditions. And they occur all over the world. They're quite rare, but they are not by any means well understood, and a lot of people do not agree as to how and why they form. But they can take a number of different forms in extremely rare circumstances, ultra huge upside down cups like this. Again, looking at below the waterline, once you get down there, all kinds of funny things can happen, especially if the waterline fluctuates. Goes up and down over time, it changes deposition, it has some dissolution, and it recharges chemicals that are growing minerals, so adds for some interesting complexity. And one of the things that happen or in shallow pools are things which I happen to be it's one of the multitude of things I'm overly interested in, are cave pearls. And so I'm going to jump to this topic. We're going to do really fast because there's cave pearls, and you would all be snoring, I'm sure, but it's But to me, amazing things. They do form a bit like pearls in oysters, except there's nothing organic about it. There is slow deposition. Many of the cave pearls will vibrate or move in some cases, so you have microscopic depositions that can take place. Also, the surface allows the cave pearl to attract calcium carbonate that's in the water, so they can grow up layer by layer the surface of the pearls, and these can become very, very pearl-like and live in these little side nests, we call them. They can be perfectly spherical, but they can also be pancake. And there's a lot of interesting questions that these bring up in terms of genesis and form. Over time, it is not uncommon for cave pearls to become encrustatory crystals of calcite, less smooth form. But here you see a few different zones or different steps within that process of evolution. One of the rarest, however, of cave pearls are the quasi-cubic cave pearls, which, of course, no oyster ever made a cubic pearl that I'm aware of, so these are quite special. And pearls, when they do begin to develop secondary crystallization, fringes, and fringes are very cool. But probably the coolest thing, and one of the biggest surprises I'm going to show you right now, is that cave pearls are almost always formed out of calcite. However, a few rare places around the world where there are some other minerals, including some phosphates and other things. This is the first time anybody, other than a few of us, have seen crystals, or not, I'm sorry, cave pearls of very rare. These are highly protected at the moment, but this is something no one else has seen. So congratulations. I haven't shown these photos to anybody yet. This is going to be published and it's going to be big news. So it's kind of like a quasi-secret, but you know, we're in Tucson, and you know what they say, what happens in Tucson stays in Tucson, you know, so it's a... And there are seas of cave pearls in a few places. This is a pool of cave pearls that's, you know, dozens of meters in diameter. These pearls are more than a meter deep, stacked up on top of each other. Why and how they end up this way, it's a whole other talk. We think we have a good understanding, but we'll be at it for a while if we try to go into it today. Gypsum is one of the other classic cave minerals. I'm sure most people are familiar with gypsum flowers and so on. And caves are well documented. They're very cool, very wonderful. We get gypsum forming in threads and strands. We get floating bits of gypsum. We got huge needles. Some of these can be a meter in length or more. The longest floating strand of gypsum, I say floating, it's a single hair of gypsum with a knot of gypsum crystals swaying on it, and it's about 8 meters in length, hanging from a ceiling. And we don't get too close to it. The heat from our bodies causes it to sway so much that we're concerned it will actually break from the impact of our own temperature. But this gives you some idea of what these, the big ones, you really can't photograph them because they're as thick as a human hair. But this gives you some idea what they're like. Gypsum needles of all sorts and sizes, they do wonderful things. And all of the gypsum forms that happen, really, a lot of it is based on the classic twinning angles of gypsum crystals. We'll get back to this with a few other examples, even though you won't be seeing them quite the same way. These are stalagmites of gypsum formed in a rather exotic way. These have central holes reaching not only all the way through the stalagmite, but several meters into the ground below them. This is New Mexico. It's a pretty interesting discovery. A lot of research is being done on this kind of thing. These are blowing gypsum vents. You have slightly different temperature air coming out of these structures, moving from lower levels within the cave, and you have gypsum being deposited along the path of moving air. And then Lechuguilla Cave, of course, where we saw some chandeliers earlier, super famous for these absolutely spectacular displays, incredibly delicate gypsum. And this in a room called the Chandelier Ballroom, which has dozens and dozens of these fantastic structures. And now everybody in the world has become familiar with Nika Cave, which is, of course, the source of what is said as being the world's largest gypsum crystals. One thing that is kind of special about this, these may actually have been, when they formed, the world's largest anhydrite. Anhydrite is less stable than gypsum in certain temperatures, but these formed at quite high temperatures. They're formed underwater. And I'm very sad to say, although the Cave of the Giant Crystals still exists, and it is possible to see some things there, the fantastic quality when we first were visiting and working in this place has been degrading a great deal. Partly because the temperature is being lowered because it's right next to a working mine where they need to air condition. Lowering the temperature, the natural environment is altering. So the crystals are becoming less clear. There's edge deformations and so on. This is basically condensation water and so on. So spectacular view of these things that most people have seen in publications is kind of going away, but it's a wonderful thing to have experienced. And will these ever be found again? Very possibly so. The environment which formed them exists many other places. But here you can see just how degenerating some of these crystals have gotten from condensing, dripping water, and changing temperature. So I don't want to be sad, but that's that. This is more the memory that many people like. Jumping back to calcite for a few moments, calcite is certainly the most ubiquitous cave mineral. And calcite forms essentially in two big clusters. You have aragonite and calcite, and the two can interact with each other quite a lot. The aragonites can get really delicate, really intricate, and structures like this where you have trees and so on are all dedicated and directed by crystals of the aragonite. And also, as we look at various things in cross-section and so on, we begin to understand a little bit about how microcrystallization directs these things. It is a very intricate process at various different levels, and it takes place on scales, very tiny scale. Here you see a whole forest of these things are roughly the size of human hairs, these individual strands of calcite. And so if you can imagine one of your hairs with a central canal through it that allowed water to go out of its tip, this is how remarkable and delicate these things are. And forgive me if I go quickly, but I'd like to try and get to several topics before everyone. Secondary minerals growing with highly hydrated calcite forms a structure we call sometimes moon milk or Milch in German. And it's a whole other sequence of things which basically is almost a perfect indicator of microorganism activity. This is something completely ununderstood and very little studied are these hanging tubes. This is a cave, again in France, where they're hollow tubes but of much larger diameter than the straws you were seeing. Very, very slender outside and with some very interesting structure on the exterior. You can see the lattice of the individual crystals and crystal bundles that have worked their ways into clusters. So anyway, just to try and touch on all kinds of topics. How old are these things? How quickly do they form? How quickly do they degenerate? What can we tell about time looking at cave minerals? Well, some calcites form very quickly. This is a cave in the Czech Republic. This is a ladder that was placed there in right around 1890. And it happened to be in a place where calcite was forming very, very quickly. And so it's encased this ladder, and so so you get the impression that calcite forms very fast. But in a lot of other conditions, it's much, much slower, and some of the size of the depositions can be so enormous that you're looking at tremendous amounts of time, even if it is in fact growing very quickly. We have done quite a lot of dating. This is a cave in the Black Hills. These are, in some cases, some of these calcites we now know, these are spar crystals. Some of these things are Ordovician in age. So they really are old. And how quickly did they form? Well, we know the conditions that they could have formed in took a long time to develop, and it took a long time for them to be exposed. We think they may be some of the oldest of these types of calcites that we're aware of right now. And calcite loves to solidify on things like muds and so on. This is a footprint, one of actually a lot of footprints in a cave in southern France. We're able to date the calcite, so that's a 22,000-year-old footprint. There are many other footprints in this cave, and we know of one visit of what we think was a single family, adult male, adult woman, and 2 children, wandered through this cave, walked over a kilometer, left their footprints in the mud. Shortly after they left the cave, and we assume they left, there was a collapse of the entrance that they had entered through. It was an entrance in a cliffside, and preserved everything. The calcite is formed on top of this material, and the discovery of a high entrance way up on top of the ridge the cave is formed in allowed the discovery at deeper levels to find these footprints. So an example of very, very slow forming calcite, where you can actually see the interface between humans and calcite rather well. Another area where we look at calcite in terms of time is in places where, this is a cave on Mallorca, where the cave though the cave is many kilometers away from the ocean, there is a lens of saline water from the ocean and fresh water, and the saline water rises and falls with the tides. And it has been doing so for an incredibly long period of time. And in fact, the cave has perfectly preserved the whole history of the Mediterranean Ocean. There are many different stands of the height or depth of the Mediterranean, the deepest one being what was called the salinity crisis, where the Mediterranean almost completely dried up. And it was so saline that most of the life in the Mediterranean died during that period. And the fluctuation of tides causes depositions at different points, and it does so by overlapping and then going below some of the formations that are pointed into the water. So consequently, this is current tide level. This is ancient tide level, where the water would have, essentially, the thickest point of this freestanding calcite was the midpoint of the tidal fluctuation, where the water is staying the longest. And the time of the extreme high tide and the extreme low tide are the shortest periods. So this is sort of a time graph or a time bar, which gives us a nice idea of what's been going on. Now people are able to look at these things with a whole lot of cool new equipment and not only analyze their dates and ages, but they're also able to look at environmental conditions. They're able to look at paleo temperatures. They're able to look at rainfall. They're able to look at a number of other things. So for ancient temperature studies, this stuff is extremely helpful. So again, here you see this type of bulbous formation at the current level. And this is roughly the midpoint of tidal fluctuation here. So I'm going to give an example of some of the kinds of research that's going on here, and I'm getting towards the end, so if everybody's still awake, I feel good. We're going to jump off into a place called Cane Cave. This is a sulfidic cave formed by rising sulfuric acids and waters from deep beneath the earth. It's also a project I worked on for the Smithsonian, and it's been in if you see the Nova special, it was about this cave and so on. It's also made big news because almost all of the scientists working on the project were women. And at that time, everybody was excited. There were women scientists going into caves. It's much more common now. In fact, I would say pretty close to an equal balance between sexes working on cave minerals, cave exploration, and so on, which I think is really a healthy and great thing. Anyway, this cave starts off rather typically, a few crawls and so on. We reach a watery passage which has fairly normal water. We would walk through it without any big deal. The only important thing to realize, though, is this water has a pH of 1, so it's highly acidic. It will, have some impact. It chews up clothing and so on. Once we're into the cave, the levels of SO2, sulfur dioxide, can get quite dangerously high. So we have warning sensors and so on. We do wear masks and so on to deal with potential problems. But we find all these really fascinating zones within the cave that don't look like other caves. This is an actively forming sulfidic cave. The waters are still rising, minerals are still being deposited and dissolved here. So we're able to look at this stuff in context. These are droplets of sulfuric acid. They are being excreted from the walls and ceiling of the cave. And we now understand that this is being done by microorganisms which are essentially eating the bedrock here. And you have sulfur oxidizing, you have sulfur reducing, a very complex process going on. As this sulfuric acid migrates into areas that have not been heavily impacted yet, it forms these snotites and other kinds of structures of semi-dissolved limestones and calcites. And so looking at this stuff and studying it, folks from the University of Texas in Austin have been able to bring in lots of cool instruments. We have gas chromatographs and so on, looking at these things and following the whole process of this life cycle of these organisms. And we're finding that not only do the microorganisms cause the rock to be eaten, the cave to grow, there's waste products of the microorganisms. The waste products are eaten by other microorganisms and so on, and we get these secondary deposits of gypsums and so on. As a result of these processes, this crystallization is driven by things that can't be seen without an electron microscope. And the other thing that we find in this cave are these elaborate and very colorful bacterial pools and colonies, which are formed in some of the pools and waterways. And they're quite spectacular and interesting things to see. These are essentially blurring the line between what we think of as inorganic minerals and life. And you can pretty well throw away most of the usual definitions about the three kingdoms, plant, animal, and mineral. At this point, they're all kind of mixed up, and especially here is a beautiful example of how they're not neat things. Just one or two other topics, if everybody can hang in. We do find in certain caves, certain flowstone floors and so on, instead of being smooth, are in fact very rugged, very triangular structures seen. These triangles can get pretty good sized. They can form in clusters and ridges and so on. This all has to do with a rather intricate balance between atmospheric ability to degas and deposition of calcium carbonate. And these things can then form these rather delicate, extremely large cups and cones and so on with triangular structures, some of which are, I think, some of the most elegant calcites on the planet. Beautiful, beautiful things. And here's just basically an incredibly simple drawing. I'm not going to go into any of the real depth of this. Folks have questions later, we can chat about it. But monocrystalline forms can continue not on not just on a floor. Hanging stalactites or stalagmites can in fact be angular in cross-section. Again, it's structure of the twinning calcium that drives this. The one on the right is a stalagmite that had formed a column. There's been a long ago subsidence earthquake most likely broke it, and here you see the triangle in cross section, which you can't see unless one of these things is broken. And then you get all these other forms that grow at the bases of typical stalagmites and so on, which are sort of an interface between the highly geometric forms and then the less geometric, in fact, non-geometric dripping forms. Hanging things which will form individual crystals, well, they're not single crystals, but they're composed of stacks of single crystals in twins. And that is more or less the conclusion of my talk. These were interesting enough that it was not about mineral collecting, but something that is dear to the heart of a number of people in the mineral world. And I thank you all for hanging around. This will, happy to chat with folks at talk if you have questions, and hope to see you around the show. I'll do my plug. We're at Mineral City. Come by and contribute to the exploration and preservation of caves by buying minerals. We love that. And thank you all for coming. Yeah.
Do you hold that?
I only did it a couple of times, but yes, I did. And people thought it was really stupid. It was stupid, actually, but it was fun to do it once, And second time was really stupid, and there hasn't been a third time.
Hey, Kevin, I've got a question.
Yeah.
And this is unusual because I usually don't ask questions in these things, but all of these things grown in caves grow without any light. So in the affects the growth or development of some of these minerals?
The answer is yes. Sometimes within sight of an entrance, especially large entrances, you can get light which will affect things. Sometimes it's preferential growth or not growth based on the light. There are also, and it's one of the many topics we didn't put in here, there are some microorganisms and actually do emit light in some caves. The worms in New Zealand are a really great example. Far into the caves, you'll have these glowworms drop down these little tendrils low, and they try to catch flying to eat them. And these glowing things are, in fact, light. Does that light really affect the cave? I don't see any evidence of it, but there is light there, rarely in certain places. Otherwise, though, it's all total darkness.
Interesting. So there'd be no chance of any emitting photons from some light source affecting something. It would have to be obviously over a significant period of time.
I would think so. I mean, obviously, we do have an impact ourselves going into any cave. Just breathing, being there. All aliens, and we're aliens there, have some sort of an impact on the environment. But we do our best to be extremely minimal in our impact. There's really no good evidence of, calcites or other minerals being affected badly by the light that we have to carry. And we don't really have super, super strong lights, except when we're making photos, and we're talking very brief moments while we flash things.
Yeah. There was a viewer online who was just blown away by the fact that the body heat could could induce a movement into those human hair thin formations.
Yeah, we are. We have to be incredibly responsible to work in these places, because it's, we're responsible for the next 100 generations what they will find and see. And so it's one of the reasons why it's super important that we leave as many of the caves as intact as possible all over the world. It's something really very special.
Thank you for what you do, Kevin. You are a true champion.
Oh, well. Thank you. Oh, well. Ay, ay, ay. You sat there with your hands the whole time. What a guy. It's like, I wouldn't do that. Oh, well, thank you for showing up. I'm glad.
That's my number one, but I didn't want to.
Let me turn off the mics here. So that was Kevin Downey doing his presentation on cave minerals. I had to get in there and ask those questions about the light, and there's so many other questions I have. I promised you something you'd never seen before. Rhodochrosite cave pearls. Blew my mind. I hope you all enjoyed seeing that. If you look over my left shoulder right there, that's Ann Fraser. And Ann Fraser is going to be one of our featured speakers in our next presentation at 2 o'clock. So that's about a little more than an hour and a half. And if you look over my right shoulder, there's Andrea Suarez, otherwise known as the Mineral Girl. So, a lot of things happening at the Tucson Fine Mineral Gallery. Tune back. Oh, there's Andrea. I forgot to turn my camera back on. So, a lot of things happening at the Tucson Fine Mineral Gallery. If you're anywhere in Tucson, come down, check out the talk. Alan Hart and Ann Fraser. Ann and I are going to go grab some lunch right now. We'll see you back at 2 o'clock. And why don't we get a little music going for you guys? All right. Take care. Thanks for tuning in.